Welcome back, Accelerated Math Analysis. Today we're doing part 2 of section 12.2. Our learning objective, our learning target is that we can solve arithmetic application problems, and in particular those involving an arithmetic sequence or a series. Let's read through number 1 here. We've got a ceramic tile floor is designed in the shape of a trapezoid. We've got 20 feet wide at the base, 10 feet wide at the top. It's pictured right here. The tiles, now immediately as you begin to read this, you can see what's happening. We've got different units. The tiles are 12 inches. So what's happening is we've got this trapezoid, but of course as we enlarge this, each individual tile here is 12 inches by 12 inches. So what we have to be aware of is that we're going to make these tiles all go in a row so that each successive row contains one less tile than the preceding row. What we're asked to do is find out how many tiles are required. Now, of course, as we're looking at this, we've got 20 feet wide. Well, we know that there are 12 inches in a foot. So 20 feet, if we were to multiply by 12 inches per 1 foot, of course, we'd have 240 inches. So we've got 240 inches of space that we're going to have to cover down below. And then our top, we've got 10 feet wide at the top. Well, if we took 10 feet times 12 inches all over 1 foot, I think we can all see that we'd have 120 inches up on the top. So we've got 120 inches of space to cover there. Now each tile is 12 inches. So maybe the big question is, let's look at this bottom row here. We know that each little tile is 12 inches, but we've got 240 inches. You might wonder how many tiles we're really using. Well, it's just some basic math. We could take 240 divided by 12, and 24 divided by 12 is 2, so you might not be too surprised to see we're going to have 20 tiles. So we're going to have 20 tiles. This is our first row. And then, we're going to actually be adding all these up. We want to find out how many tiles are all together. But, in a sequence, we'd have 20. Well, our next row then would be, 19. How do we know that? Each consecutive row, each successive row is one less tile. And then we'd go to our third row. We know that we'd be at 18 tiles. And we're going to keep going until we get to the top. And the top, of course, if we've got 120 inches of space, but each one of these tiles is 12 inches, take 120, divide by 12. You can see very quickly you have 10. So this is our last row. And we're going to be adding this up. So we can see very quickly what is really happening. We're going to be able to more or less know that we're adding up a certain number of rows. You can wonder how many rows that really is. Well, we've got a sub n is equal to a sub 1 plus n minus 1 times d. We know that the last term in this pattern is a 10. The first term is going to be a 20. We know that our d is equal to negative 1. We might wonder what term we are winding up with at the very end. Tell you what, I'm going to minus a 20 right here. 10 minus 20 is negative 10. And at this point, I'm actually going to divide both sides by a negative 1. To have 10 is equal to n minus 1. And that would lead us to be able to say n is equal to 11. So this is our 11th row. Another way to look at this is a sub 11 is 10. So now I know that I am, in fact, adding up 11 terms in this arithmetic sequence. What we can do is go back to Baby Gauss's formula. S sub n was equal to n over 2 times a sub 1 plus a sub n. we know that n is going to be 11. So we could say s sub n is going to be 11 all over 2. What's my first term? Well, my first term is a 20. What's my last term? Well, it's going to be a 10. And 10 plus 20 is going to be 30. So, and forgive me, we could actually now say this is s sub 11 right here. We now know that we've added that up. So we've got 11 over 2 times a 30. 2 goes into 30 15 times. 15 times 11, you're going to work out to 165. That's 165 tiles. And we're done with question number 1. Looking at problem 2, we can see that we're given an arithmetic sequence, but it's written very abstractly. Our first term, we don't have a specific number. We're just told it's 2x. The second term is 3x plus 2, and this third term, it very well will continue on, but this third term is 5x plus 3. And as we wrestle with this, we can think, well, how in the world can we find x? Well, remember that your common difference must be the same. 3x plus 2 minus 2x. Here are consecutive terms, and if we were to work that out, we'd get that d is going to equal, well, 3x minus 2x is just 1x, and that's x plus 2. But of course, we could also have looked at the consecutive terms of 5x plus 3 and 3x plus 2. We looked at that third term and the second term. If I were to subtract, distributing this negative, we'd see that that common difference, 5x minus 3x here would be a 2x, and 3 and a negative 2 would just be a 1. Well, we know that these common differences must be equal. They must, in fact, be the same. So as we set this up, and if we subtract an x from both sides, and then if we very simply subtract a 1, we'll come up with x is equal to 1. And by the way, you can always double check if you've done this right. If that were the case, the first term, 2 times 1 would be a 2. 3 times 1 is 3. 3 plus 2 would be a 5. And you plug in a 1 into this last term. 5 times 1 is 5. 5 plus 3 is 8. So you'd have 2, 5, and 8. You could see, yes, in fact, you do have what appears to be an arithmetic sequence. Your common difference would be a 3. Again, we're asked to find x to make that happen. All right, last problem. How many terms must be added in an arithmetic sequence whose first term is 78 and whose common difference is negative 4 to obtain a sum of 702? Well, remember that from our lesson yesterday, we saw that there were 2 formulas we could have for adding up the sums in an arithmetic sequence. The first one in the box was actually right here, where we didn't know the nth term. And we're not given that last nth term here. We just know the first term is 78. We're kindly told that the common difference is negative 4. But from here, we don't have much else except to know what the sum is. We want to know the number of terms. We're trying to find n. We're trying to find n to make this happen. So s sub n, that sum is 702. I don't know n. I'm looking for it. I have n over 2. My first term is actually 78. So I'll have 2 times 78. Then I've got this n minus 1. I don't know n, so I don't know what n minus 1 is. But then my common difference would be negative 4. Right now, you can hopefully see that we can, in fact, solve this problem. It's just that we're going to have to realize, if you're on your toes, you're going to see we're going to have a quadratic. First things first, I want to get rid of this little fraction. I'm going to multiply both sides by 2. And that's a smart thing to do. You can quickly see that you'll get 1404 on this left side. The right side, you'll just have an n. And 2 times 78 would be 156. As I distribute -4 here, we'd get -4n, and -4 times -1 is a +4. So cleaning this up a little bit, just combining our like terms inside of our brackets, we'd have 156 plus 4 is 160. And like I said, you're going to see that you have a quadratic. You've got 1404 is equal to, as I distribute, 160n minus 4n squared. Well, when we're solving a quadratic, it can be helpful to get all of your terms on one side. I'm going to add a 4n squared, simultaneously subtract a 160n. And right now, my goodness, we very well have a messy looking problem with some frighteningly big numbers. But I am noticing that I could divide out a 4 from all of these. Remember that if your last 2 digits of a number are divisible by 4, that means that the number itself is divisible by 4. So if I divide everything by 4, I'll have n squared. 160 divided by 4 is 140. And then over here, I believe you'd get 351 as you would divide that out by 4. So, at this point, factoring is a possibility, but these numbers are rather obscure. I hope you do have the quadratic formula built into your computer programs. We'll do that right now. Press Program, Execute Q, and we could see that our A is going to be a 1. And again, we know that A is equal to 1 because that's the coefficient in front of n squared. Our B would be a -40, and our C would be 351. So, as we work this out, hopefully it will just take a moment to have us finish up. We know that we are expecting our term number to not be a decimal or a fraction. We also don't want our term number to be negative. Surprisingly, there are 2 possibilities for this to happen. N could equal 27, or n could equal 13. That is a real possibility. We could see that as we are adding this common difference, perhaps there will be 2 times when our sum will actually arrive at 702. Best of luck to you.